Hello, our viewers. Previously on our discussion, we have tried to see about wave optics. We have tried to define what wave optics is, and we have tried to see some of the properties of light using wave properties, corpuscular theories, and so on. So mainly we just focus only on wave nature of light. And today we'll try to see about electrostatics. Here, under this unit, we'll try to see about electrostatics. Actually, electricity can be classified as electrostatics and electrodynamics. Electrostatics is the study of charges which are at rest or sometimes known to be having random motion. And we'll try to see those natures. So electricity is a branch of physics. We know that it studies about charges in general, and it can be further classified as electrodynamics and electrostatics. Electrostatics is the study of charges having random motion. We call it to be at rest. So what do you mean by charges? Well, charges like one of the nature of or properties of matter. For example, mass is a property of a massive body. Momentum is a property of a matter or massive body. Inertia and so on. Like that, charge is also a property of a matter in which a given matter or object is immersed into electromagnetic field. The electromagnetic field will exert electromagnetic force on that matter so that that matter contains the charge nature. Actually, all matter has charge property except photons, so that it's possible to explain this. There are only two charges in nature, and these are positive and negative charges. We know that this is true. And the smallest charge ever exists so far is the charge found on electrons and protons, except quarks having 1/3 of the charge. But mainly, we have found that the charge on electrons and protons is to be 1.6 times 10 to the power of minus 19 coulomb. Minus sign used to represent the electrons, and plus sign is used to represent the protons. And charges are quantized. This is a very important concept or characteristics of charges, meaning that they are the integral multiple of the smallest amount of the charges, and mathematically can be expressed as charge Q is n times Q, where n is the integral, okay? The integral number, plus or minus, might be electrons or protons, so that -1, -2, +1, +2, and so on. Times the multiplication of this smallest amount of charge. These are the properties of the charge, and materials, depending on the number of those charges, can be classified as neutral and charged body. Neutral bodies consist equal number of protons and electrons, whereas charged bodies consist unequal number of electrons and protons. There can be a negatively charged bodies and positively charged bodies. Negatively charged bodies consists more electrons than protons, and positively charged body consists less number of electrons than protons. It's possible to convert one into the other. Neutral bodies can be converted into charged bodies, or charged bodies can be converted into neutral bodies. Charged bodies can be converted into neutral bodies by a technique of discharging, whereas neutral bodies can be converted into charged bodies by a technique of charging. There can be conduction and induction technique. Actually, conduction is charging by rubbing, or it might be charging by contact, whereas induction use additional techniques of grounding techniques without actual contact between the charged bodies. So these are the properties of the materials. And there are different laws of about charges. When you are trying to study about charges, you should have to know the characteristics of the charges. And among that, the law of conservation of charges states that charge is neither created nor destroyed, but is a transfer from one body to the other. This is what it says. And we have law of electrostatics, and it says that like charges repel each other, whereas unlike charges attract to each other. There are different laws concerning on the property of charges. Now let's try to see what is around the charged body. And around any charged body, there is a field, or there is a region. And that region is a region where we detect electric force, and it's known to be electric field. So it's a region found around any charged body. It might be plus or minus charged body, so that there will be a region where you can detect the electric force. So this is known to be electric field, and electric field can be represented using imaginary lines known to be electric field lines or electric force of lines. And these field lines has their own properties. And the first properties, they run out from positive and run into negative. Actually, this property is arrived because of that there is a conventional test charge known to be a smaller charge, which is a positive test charge. Using a positive test charge, it's possible to find those properties. For example, if you have a positive charge, a main charge, and if you brought a positive test charge, a smaller charge nearer to this main charge, this charge from the law of electrostatics tries to push the charge away. So this test charge, since it is positive, it's moving away from the charge. So that you have to draw the electric field lines always away from positive charge. And if you have a negative main charge, so if you brought the test charge here, the negative charge will attract towards it. So that the direction shows us you should have to draw the electric field lines towards the negative charged body. So among the properties of field lines, this is what it says. They run out from positive and run into negative. They never cross one another. As you draw the electric field lines, you should not have to cross one another. And they are denser at sharper edge. For example, if you have perfect sphere might be having a positive charge or negative charge. If you have irregular shaped bodies like this, there will be higher, denser field lines should be drawn at sharper edge, and there will be a less denser field lines drawn at smooth edge. These are the properties of electric field lines. And now let's try to see about the mathematical expression of electric field. Electric field strength, actually it is a measure of the amount of or the strength of a given charge to exert force onto the other charges. Suppose here you do have a main charge and here you do have a test charge. So we measure the strength of this charge to exert force on the test charge. Okay, to exert force means either to pull or to push. For example, if this is positive, we know that the test charge is positive, so that this charge tends to push the test charge. So electric field strength is measured using E is equals to the electrostatic force F over the test charge. This is a mathematical expression of electric field strength, and its SI units is expressed as Newton per Coulomb. And there is another unit known to be volt per meter, so that the standard unit, the SI unit, is Newton per Coulomb. Keep this in your mind. So how do we express force? The electrostatic force mathematically can be expressed using Coulomb's law. Augustin de Coulomb proposed a law which is similar or analogous to that of universal gravitational law expressed by Sir Isaac Newton. So that here, if you have two charges, actually those charges might be charge 1 and charge 2. You can say this is charge 1 and this is charge 2. In this case, the test charge and the main charge. Okay, the test charge and the main charge. So the electrostatic force, the interactive force, has a direct proportionality with the multiplication of the two charges. So F has a direct correspondent with the product of the two charges. And it has inverse relation with the square of the separation distance between the two charges. For example, if the distance is expressed as R, the electrostatic force has inverse relation with that of the gap between the two charges. So mathematically, when you express this one, it has a direct relation with the product of the charge, and has inverse relation with that of the square of the separation distance. When you convert this into equation, you should have to introduce K, the proportionality constant K, known to be Coulomb's constant. They measure properties of something like medium or objects. In this case, K, Coulomb's constant, is a proportionality constant known to be Coulomb's constant, which depends on the further permittivity of free space. Here, the permittivity of the space, the free space, to allow charge interaction. And it further can be expressed as 1 over 4 pi epsilon naught. Epsilon naught is known to be the permittivity of free space. And if you substitute the permittivity of free space is 8.85 times 10 to the power of minus 12 Coulomb squared, Newton meter squared, so that if you substitute this, you can find the Coulomb's constant to be 9 times 10 to the power of 9 Newton meter square per Coulomb squared. So if you substitute here, you can find the electrostatic force F is equals to K times Q1 Q2 over R squared. So this is a very important equation used to express the interactive force between 2 point charges. So using this equation, it's possible to find the electric field strength, because that's the electrostatic force can be expressed as kq1 q2 over r squared. In this case, q1 is the main charge q, q2 is the test charge. So if you substitute using the main charge k and the q and the test charge q naught over r squared. This is how we express the force between the main charge and the test charge. And previously we have said that electric field strength can be given as force over test charge. But in this case, we know that electric field strength is independent of the strength of the test charge. Okay? The strength of the main charge is independent of the test charge at a given point. Therefore, if you substitute the force over here, you can find electrostatic field as kq, the test charge q, over r squared, over the test charge q naught. You can eliminate q naught here. So clearly you can see that electric field strength is independent of the test charge. Rather, it depends on the strength of the main charge and the distance between the main charge and the location where the test charge is kept. So keep this in your mind. Electric field is independent of the test charge. So here, students, I want you to try to solve this. For example, how strong an electric field strength is at 3 centimeter from 24 microcoulomb of charge. So it's possible to use 24 microcoulomb of charge is the main charge. K is already given, and the separation distance is given to be 3 centimeter, so that R can be given to be 0.03 or 3 times 10 to the power of minus 2 meter. So substituting this, you can find the electric field strength. You can find the electrostatic force between two different charges, electrons and protons, and so on. So I want you to solve this problem. Now let's try to see the motion of charged particles in a uniform field. It's possible to have charged particles moving or launched in a uniform field, parallel to the field or opposite to the field. For example, in this case, if you are trying to propagate, if you place a positive test charge, we know that there might be a positive charge or a negative charge here. Let's take a positive charge. So as this positive charge is released in a uniform field, let's have two plates, plus and minus plates. As these two plates are opposite, there will be electric field strength. And the electric field strength, as we have previously mentioned, should be drawn from positive to the negative. So the direction of the electric field strength is from positive to negative. If you put a test charge here or a single point charge here, this charge is tending to move parallel to the field. So a positive charge always moves along the direction of the electric field. A negative charge is always moving opposite to the direction of the negative field. If you put a negative charge here, this charge is tending to move opposite to the direction of the electric field. Actually, this is negative, this is positive. The negative one pushed it, whereas the positive one attracted it toward the seats, so that the direction of the negative charge is opposite to the field, and the direction of the positive charge is parallel to the field. Now the question is, you can possibly study the kinematics of these charged particles. As it moves, what will be the acceleration, the velocity, the time it took, the displacement, and so on. It's possible to express that. In this case, the only force which is acting on this charged particle is, we know that electric field strength can be given as force over charge Q. From this, the electrostatic force can be mathematically expressed as the electric field strength times Q. So here you have a uniform electric field, external electric field E, and here you have the charge Q. So multiplying the charge Q with that of the uniform electric field E, you can find the net force exerted on this point charge. So we know that from the concept of dynamics, net force can be expressed as mass times acceleration here from the law of Newton's law of motion. And the net force appears due to the electric field strength E times Q. Expressing this, you can find the acceleration of the charged body as the uniform electric field times the charge Q over the mass of the charge here. It might be protons, electrons, or any other charge, so that it can have such an expression for the acceleration. So if you find the acceleration, it's possible to find the displacement, it's possible to find the initial, the final velocity, the time it took, and so on. So it's possible to find that, and as well it's possible to find the speed of this charged particle as it tends to move and kicks with that of the negative plate. For example, if you put the positive charge here, if you released it, initially the initial velocity is 0, and it propagates or accelerates in this direction and collides with this plate. So what is the final velocity as it strikes the opposite plate? And it can be given from work energy concept, so that work energy theorem can be expressed using this. Twice of the electric field E, Q, the distance between the two plates can be expressed over m. Okay, this is the final velocity of the charged particle as it strikes the other plates. And the other thing is, it's possible to launch the charged particles parallel to the field. For example, here you have a positive plate and a negative plate, so that the direction of the electric field is always from positive to negative. And if you launch the charged particles perpendicular to the field, we know that positive charge are tending to move along the field. But in this case, it's not going to move directly to the field, but it's gradually bending and forms a projectile motion. So that the horizontal velocity, as we have discussed in projectile motion, the velocity remains constant for horizontal projection. So the horizontal velocity Vx remains v. There is a downward velocity, it might be expressed as a times t. So you can find the mathematical expression. And at last, as it twists and moves out from the field, there will be an angle theta, angle of deflection, known to be tan theta. So it's possible to express the final velocity v mathematically, square root of the electric field, the uniform electric field of this, times the charge q, the distance where it took here d, okay, and over mass times tan theta, the angle of deflection, and the mass of the charge is possibly expressed using this equation. This is true as the charged particle is moving perpendicular to the field. Previously, what we have discussed here is as the charged particle is moving parallel to the field, in this case parallel to the field. And now let's try to see about Gauss' law. Okay, so far it's possible to find the electric field strength from a single point charge using Coulomb's law. But what if we have different shape and different concentration of charged bodies on different bodies? It might be you have a rod, and you might have a uniform charge distribution on a rod. You might have a plate, on a plate, a uniform charge distribution, and so on. It's possible to use a law known to be Gauss' law. And it says that the electric flux is proportional to the enclosed charge. This is what Gauss' law states. But what do you mean by electric flux? Electric flux can be expressed using a Greek letter phi, and electric flux is a measure of amount of number of electric field lines which penetrates a given cross-sectional area. So it's a measure of number of field lines which penetrates a given cross-sectional area. And that cross-sectional area, for example, if you have a point charge at a distance of r from this point charge, you can have a spherical surface area. And these electric field lines will be merged from positive lines, so that from positive charge it might be radiating out and penetrates the electric ideal surface. So the number of field lines which penetrates this surface is measured using electric flux phi, and mathematically it's a dot product of electric field and the cross-sectional area. EA cosine of theta, this is what it says. And the SI unit of electric flux can be given as Newton per Coulomb. This is what it says. And the imaginary surface can be spherical, different. We can have different types of surface. This surface is known to be Gaussian surface. It's imaginary surface used to determine the shape or used to determine the electric field around any types of charged bodies. For example, if you have a rod, you can take a spherical Gaussian surface. If you have plate like this, you can take a rectangular or cubic Gaussian surface. It's imaginary surface, so that's possible to find the electric field strength. And mathematically, it can be expressed that the flux phi is correlated with that of the enclosed charge. In a given imaginary surface, you can enclose the certain or the total amount of the charge. So flux phi has a direct correspondent with that of the enclosed charge. The enclosed mean the enclosed by the imaginary surface. And the consequence of Gauss' law on electrostatic equilibrium conductors can be stated here. Suppose you have a conductor. On that conductor, let's take a spherical might be conductor, and conductors have free electrons, so that the free electrons are moving and scattering on the surface of the charged body. And it's known to be electrostatic equilibrium. Conductors reach in electrostatic equilibrium. So the properties of conductors, it might be a metallic sphere, reach in electrostatic equilibrium has the following properties. And these properties is there is no electric field inside the conductor. If you enclose here using a spherical Gaussian surface, you can't find any electric field strings in the conductor. If it is non-conducting material, it's possible you can find net charge might be found here. But for conductors, you cannot find net charge. The net charge might be 0. And if there is a free charge, the free charge will be scattered or reside on the surface. This is a property of the conductor. So the electric field is 0 everywhere inside the conductor. If an isolated conductor carries a net free charge, that charge will be reside on the surface, as I said previously. And the electric field just outside just on the surface is the maximum electric field strength, so that the electric field can be given using sigma over epsilon naught. This is the surface charge density. There is a term known to be surface charge density, and there is also linear charge density and volumetric charge density and so on. For an irregular shaped conductors, as I said earlier, for example, if you have irregular shaped conductor, for electric field lines are drawn denser at sharper edge and less denser at smooth edge. In this case, for example, if this is a sharper edge, the charges are more resides here. But for a smoother edge, the charges are moving, scattering less denser. This is the property of electrostatic conductor. Now let's try to see about electric potential, potential difference, and electric potential energy. For example, here, if you have a charge, and if this charge is moving from point A to point B in a uniform electric field here, and this uniform electric field E, and here you have Q, the amount of the charge, and the charge has its own mass m. So as this charged body is moving from point A to point B, the electric field strengths are going to perform work, and this work is known to be electric work. So the electric or electrical work, for as it drifts this charged body from A to B, can be given as, we know that work is expressed as force times displacement. And the force is expressed as, since it is a uniform electric field, and a uniform electric field E times Q, and S is the distance where it drifts from point A to point B, D. So this is how we determine the work, the electrical work performed in a uniform electric field. For example, if you have point charge as a source, and if you have test charge from point A to another point B here, if it is drifted like this, you can express the distance from this to this, R at point B, and the distance from this to this as R at point A. So that the distance D is known to be the difference of RB, R at B, at location B, minus R at location A. It's possible to express this, and sometimes D can be expressed as change in R for point charges. So if you put this like this, work is equals to E times Q, the uniform charge times Q. The distance between A and B can be expressed as change in R. Or instead of change in R, you can possibly substitute it as EQ R at point B minus R at point A. You can find like this. And the multiplication of EQR at A minus EQR at B, for example, like this. The difference of these two, EQR at A minus EQR at B, enables us to perform work. As we have discussed in work energy concept, the difference in energy enables us to perform work. We know that energy is the ability or the capacity to do work. So in this case, the difference of something enables us to perform work, and the difference of that is known to be energy. And this energy is known to be electrical potential energy, and electrical potential energy at a specified point can be expressed as EQR. It's also possible to express for a point charge, electric field strengths can be given as K, Q over R squared, as we have previously mentioned. It's possible to express electrical potential energy as KQ, small q, the test charge over R. Okay, here you have the main charge Q at a distance of R. You can have test charge Q, so that the electrical potential energy exerted on this charge U can be expressed KQ. Q means the main charge, the capital Q, small q, the test charge over R. It's also possible to find electrical potential energy of different charges. For example, here you have the assemblation of these different charges. Those three charges stays here, meaning that there is a mechanical work performed to gather all those charges and put them at this location. So the electrical potential energy due to several charges can be expressed using this equation, and the electrical potential energy due to a single charge K1, Q2, here Q1, Q2, and the distance between the two charges over R1, 2. Here Q1 and Q3, you can multiply Q1, Q3, and the distance between the two, Q2, Q3, the two charges multiplied by their distance. This is how we multiply the net electrical potential energy required to perform work from infinite distance to a place where they are found now. Okay, to assemble and hold them at this location, we require such amount of electrical potential energy. And what do you mean by electric potential then? So far we are trying to deal with electrical work and electrical potential energy. And here there is a term known to be electrical potential or just potential. Electrical potential is a measure of potential energy per charge. It is somehow analogous to that of electric field strength. Previously, at a specified point, we are asked to find electric field strength. Electric field strength is a measure of the strength of this charge to exert electric force onto the test charge. Like that, electric potential means the potential of this charge to exert electrical potential energy on the test charge. Previously, we have said that electric field strength is independent of the test charge. The same is true. Electric potential is independent of the test charge again, because that electrical potential energy can be expressed as KQ, the main charge, the test charge over R. If you substitute here, you can find that electrical potential is clearly independent of the test charge, KQ over R. For different types of charge, it's possible to use the summation of the charges like K times Qi's over Ri's. If you have two or more charges, it's possible to find it like K Q1 over R1 plus Q2 over R2 and so on. It's possible to find the total potential of due to several charges. Potential difference. Now the potential difference is the difference in electric potential between two interval of points. So in this case, potential difference between 2 points on point charge, okay, can be expressed as the potential at point P minus the potential at point A. For example, here you have the main charge, here you would have 2 points. If you put the test charge here and if you put the test charge here, there will be a difference in electric potential. The potential here and the potential here are totally different. So we are asking to find the potential difference between 2 points. So potential difference measures the difference in electric potential between two locations, and it's very important. Sometimes in electrodynamics it's known to be voltage. Okay, we call it to be voltage or potential difference for point charge systems. And here electric potential can be mathematically expressed using a dot product of two vectors. Here electric field strength is vector, R is as well as a vector. It's possible to use the dot products of displacement and electric field strengths so that you can express the potential. So electric field dots with R can be given as electric potential. And at last, let's try to see about one of the important device, electrostatic device, known to be capacitor. Capacitor is a device used to store charges, or sometimes known to be capacitor is a device used to store electrical potential energy in the form of electric field strengths. Capacitor is made of two parallel plates and an insulator between it. The insulator is known to be dielectrics or it might be air, it might be mica, paper, wood, whatsoever. There will be insulator between it, and the two plates are connected with a source, plus source and minus source, so that charged particles are drifting and stored on the opposite plates, the plus charge on the positive plate and minus charge on the minus plate. Capacitors can be symbolized by using two parallel plates like this. If you find like this, it's a capacitor. But if you find one longer and the other is shorter, it's source. Okay, plus and minus source. This is known to be cell for a single one, and you can have such series of longer and shorter lines. This is known to be battery, which is a plural of cell. This is for cell, and this is for battery, and this is for capacitor. So if you try to connect capacitor with a source, like this one, symbolically it's possible to express it like this. The capacitor connected with the source. So the plus sign is going to drift the electrons from this plate. For example, if this plate has plus minus neutral bodies, it's going to draw, since it is a positive charge, it's going to draw the electrons out from this. So as the electrons are tending to move and accumulate on the other plates, the place they left here becomes positive. So that this plate is positive, the other plate is going to be a negative plate. This is how capacitor works. And it stores energy as far as that the source, the voltage of the source, is equals to the potential difference formed between the plates. The potential difference of the capacitor, let's call it VC or just V, the voltage or the potential difference between the parallel plates is equals to that of the voltage of the source. This point is known to be saturation point, the point where storing charge stops. So till it reaches to the saturation point, charging proceeds. As it reaches to saturation point, meaning the potential difference between the plates of the capacitor is equal to that of the source, so charging stops here. And the amount of the charge here, as the amount of the charge is increasing and increasing, the potential difference or the voltage here is going to be also as well increase. So the amount of charge Q has a direct proportionality with the potential difference formed. And you can convert this into equation. Q is equal to a certain proportionality constant K times V. And this proportionality constant K is always measures the property of objects and enables us the capacity of a capacitor to store charges. And it is known to be capacitance. And it's symbolized as C. So capacitance C is Q over V, the amount of the charge stored over the potential difference formed between the parallel plates V. And capacitance is independent of the amount of the charge stored. Here, if the amount of the charge is increased, the amount of the charge stored on the capacitor, the increment and the decrement of the charge doesn't affect. Actually, capacitance of a given capacitor depends on the geometrical property of the material. Meaning it depends on the area, on the gap between the plates and the materials that we put in between the plates, known to be dielectrics. Those are the factors which affect capacitance. But mathematically here it says Q over V, and the units for capacitor or capacitance is coulomb per volt. So coulomb per volt is farad, it's known to be farad, so 1 farad is equal to 1 coulomb per volt. So capacitance of a capacitor is independent of the amount of the charge. Rather, it depends on the geometrical properties of the capacitor. So it depends on the permittivity of free space, meaning between the plates, what kind of materials are inserted. Is it air? If it is air, you can use permittivity of free space. And if it is here, like wood or mica or any other dielectric, you should have to put the dielectric constant, or known to be relative permittivity, K. So the main factors affecting one is the dielectric constant, the other is the area of the plate. The area of the plate, and the other thing is the gap between the parallel plates affects the amount of the charge stored on the capacitor, or known to be the capacitance. So the capacitance depends on these geometrical properties of the material. And now let's try to see about the combination of capacitors. Two or more capacitors might be combined seriously in parallel combinations. Here we can have a series combination as well as a parallel combination. Series combinations meaning you should have to connect end to end of those capacitors. If you have 3 capacitors like here, C1, C2 and C3, you should have to connect each capacitors plus, minus and so on. Okay, plus, minus like this. You should have to connect all those capacitors alternately. End to end connection is known to be a series combination. Plus, minus, the source plus and the source minus. And for capacitor connected in series, the amount of the charge stored on each capacitor remains constant. And the total capacitance of a given capacitor connected in series is the reciprocal sum. Meaning the capacitance of capacitor 1, capacitor 2, capacitor 3 can be given as C1, C2 and C3. So total capacitance, the effective capacitance can be given as the reciprocal sum of the capacitor, reciprocal sum. Like this. Should have to invert it, 1 over C1, 1 over C2 and so on. The total capacitance, 1 over C. Don't forget this one, 1 over C can be given as 1 over C1 plus 1 over C2 plus 1 over C3 and so on. This is how we determine the total capacitance of capacitors connected in series. For only 2 capacitors connected in series, it's possible to have a very small or easier equation. For only 2 capacitors, it's possible to have 1 over C is equals to 1 over C1 plus 1 over C2. The multiplication of C1 and C2 gives us C1, C2. So as C1, C2 divided by C1 gives you C2 plus C1. So when you convert this one, you can find the equivalent capacitor as C1, C2 over C1 plus C2. For only 2 capacitors connected in series can be given using this equation. But for more than 2 capacitors or 3 or more than 3 capacitors, it should be given as reciprocal sum. Now let's try to see about the capacitors connected in parallel. In parallel means they should have to connect side by side. All the terminals should be connected together. Plus as well with the source plus, minus with the source minus. Such connection is known to be side by side connection or known to be parallel combinations of capacitors. As capacitors are connected, the amount of charge here might be distributed in all parts. On each junction, it will be distributed. So that the charge stored on each capacitor gives us the total amount of charge. Whereas when we consider about the voltage, since they have the same terminals are connected together, the amount of the voltage dropped on each capacitor remains constant. The voltage here, here and here are all the same. But the charge is different so that the summation of those charges stored on each capacitor gives us the total amount of the charge. And to find the total capacitance of the capacitor, the total amount of the capacitor is given to be C1 plus C2 plus C3. The summation of the linear sum of each capacitor gives us the total result of the capacitance. This is a very important equation, and you should have to solve some more examples on these points. For example, here let's try to solve one good example, and it says 2 capacitors C1 and C2 are connected in parallel, and the resulting combination is connected to a 10 volt battery. Here it says C1, capacitor C1 and C2 are connected all together in parallel, meaning the plus sign with the plus sign, the minus sign with minus sign, as well with the source. Okay, if you are trying to connect like this, plus minus, meaning this source is going to draw the negative charge from this place so that this place has a positive charge, and the charge are going to be distributed here, the negative charge, the electrons, so that these plates are going to be negative. So keeping this in your mind, the capacitance of capacitor 1 is 8 microfarad, and the capacitor 2 is 12 microfarad. Here you have a source, 10 volt. Now the question is, what is the equivalent capacitance of these two? Well, for 2 capacitors connected in parallel is a linear sum. We just add to these 2 capacitors, but if it was series combination, we need to have it a reciprocal sum, or you should have to use C1 C2 over C1 plus C2. But in this case, since it is a parallel combination, you should have to use C1 plus C2, meaning 8 microfarad plus 12 microfarad gives us 20 microfarad is the total capacitance of the capacitor, or the equivalent capacitance of the capacitor. This is how we determine the total capacitance. What is equivalent capacitance? The potential difference across each capacitor, the charge stored on each capacitor can be determined. For example, if you need to determine the total voltage, the voltage on each capacitor, it's so easy since the two capacitors are connected in parallel. We know that each capacitor has the same voltage as that of the source. So the voltage drop on capacitor 1 is the same as that of 10 volt. Again, for capacitor 2 is 10 volt. Because we have said that for parallel capacitors, the voltage remains constant. Whereas the charge stored on each capacitor can be determined using the equation, capacitor equation, C is equals to Q over V. We need to find the charge Q. Q is C times V. So you should have to multiply the capacitor with that of the potential difference. So the charge stored on capacitor 1, Q1, can be given as C1, V1. We know that C1 is 8 microfarad multiplied by 10 volt gives us 80 microcoulomb. Okay, 80 microcoulomb is the amount of the charge stored on the main charge and on the capacitor 1, and the charge stored on the capacitor 2 can be given as C2 V2. So multiplying 12 microfarad by 10 gives us 120 microcoulomb. So it says 12 microfarad multiplied by 10 volt gives us 120 microcoulomb of charge. This is how we determine the amount of charge stored on each capacitor and the amount of voltage dropped on each capacitor. So students, I want you to try to solve as many problems as you can on this case so that you can develop skill of how to solve such problems. And at last, let's try to see about the energy stored on the capacitor. As I said earlier, capacitor is a device used to store charges in the form of electric field strings. So capacitor can be given as U is equals to, U can be generally given as Q squared over 2i of C, one of the case, or capacitance can be given as 1 over 2 Q times V. It's all determined from work energy concept, the integration of du is equals to V times dq and so on. And at last, keep in your mind those problems, Q squared over twice of C, or 1 over 2 Q times V, or at last, very important equation is this one. We usually use this equation, 1 over 2, the capacitance of the capacitor and the potential difference between the plates gives us the energy stored in the capacitor. So capacitance depends on the geometrical property of capacitor, K E naught A over D. Substituting this on the capacitance, and we know that the voltage V can be given as E times D previously. I have said that potential difference can be given as the dot product of E dot R for point charges, but for two parallel plates, R means the distance between the two plates. Instead of using R, you can use D. So the potential difference can be given as electric field strength times D. So substituting all those values, you can find energy stored in the capacitor as 1 over 2 K E naught A D electric field strength squared. Look here, all those properties are constant for a given capacitor. The area is not going to be changed for a given capacitor. The gap between the plates are not going to be changed. The only factor which affects is the electric field strength, so that electric potential energy is associated with that of the electric field strength squared. Actually, if you increase distance, if you increase area, if you replace the dielectrics with other types of dielectrics with higher dielectric constants, with less dielectric constants, the energy might be affected. So that the electrical potential energy stored in the capacitor can be associated like this, and that's why we define capacitor as the device used to store charges in the form of electric field strengths. So students, this is all that I've got for today. እንግዲህ ተማሪዎች ሌሰናችንን በዚህ አጠናቀናል። እንግዲህ መልካም ፈተና እንመኝላችኋለሁ። እንግዲህ ጠንክራችሁ እንድትሰሩ እመኛለሁ ጥያቄዎችን አብዝታችሁ የናሽናል ጥያቄዎችን የኢንትራንስ ኤግዛም ጥያቄዎችን በመስራት ስኪሎችን ዴቨሎፕ እንድታደርጉ እመኛለሁ መልካም ውጤት ለሁላችሁም እንዲገጥም አስባለሁ እመኛለሁ መልካም ጊዜ